If I slide this magnet past a copper ring, the ring reacts, yet nothing touches, nothing connects, and still energy moves. That's the part that messes with people. Because your brain wants two options. Either something touches and pushes like a hand pushing a door, or something shoots across space and hits like throwing a ball. But a magnet and a ring can sit separated by air, and the ring behaves as if it received a message. It can even heat up. It can even push back. And the more you stare at it, the more you feel a little cheated, because you were never told what's actually traveling. So let's do this the hard way, the honest way. We're going to build an explanation that doesn't rely on hidden magic. Not fields are just there, okay? Not Maxwell's equations say so. We'll use those ideas, but only after we earn them. We'll make a deal. We're going to explain electromagnetism as if we're trying to convince a stubborn friend who keeps asking, yes, but what is the mechanism? Most explanations secretly ask you to accept two kinds of magic, action at a distance and equations that just work. Action at a distance is the old idea that charges and magnets reach across space and tug on things directly. And the equations are usually introduced like spells. Write them down, accept them, and you'll get answers on homework. That's not understanding. That's just being trained. Understanding starts with a simple question. If I place a tiny test charge at some point in space, what determines how it will move next? Not what determines its fate in the universe, just the next instant, the immediate acceleration. Because acceleration is what forces do. A force is not a philosophy. A force is a measurable push or pull. And for electric charges, that push can exist even when nothing touches. So we define something very practical. At every point in space, we can ask, if I put a positive test charge here, what force per charge would it feel? That answer is a vector. It has a direction and a magnitude. That vector is what we call the electric field. The electric field is not a poetic idea. It's a bookkeeping device for forces. It's the simplest thing you can write down locally so you don't have to keep reciting where every other charge in the universe is. And now here's the first reason this isn't just a trick. Suppose you have two charges. You can compute the force between them directly, sure. But what if you have 1,000 charges, or 1,000,000,000? The direct every pair talks to every pair description becomes impossible to think with, but the field description stays manageable. Each charge contributes to a field, and the fields add. Then a test charge feels the field at its location. That's it. This idea of adding is crucial. If you double the sources, you double the field. If you have two sources, the total field is just the sum. This linearity is why the field concept is powerful. It turns a tangled web of interactions into a clean local rule. Learn the field at a point, and you know the force on a charge at that point. So far, this just sounds like a clever rewrite. But then you do something that makes the rewrite feel like reality. You ask how the field changes when things move, because charges don't stay still. Currents flow, magnets move. And the universe has a speed limit. Influence does not propagate instantly. You might think that's obvious today because we've heard speed of light since childhood, but emotionally, we still expect instant updates. If I wiggle a charge here, it feels like the entire space should immediately know, yet it doesn't. If changes traveled instantly, you could send signals infinitely fast, violate causality, and all sorts of paradoxes would erupt. So we need a local story that respects the speed limit, and this is where electromagnetism becomes one unified thing. The moment you demand locality and a finite propagation speed, you're basically forced into something like Maxwell's framework. But we're not jumping there yet. We're going to earn it by walking through the weirdness. Let's make a deal. You're only allowed to use what happens right here at one point in space to predict the next instant. This deal sounds restrictive, but it's the way nature seems to work. A particle doesn't consult the whole universe to decide how to accelerate. It responds to what's at its location, the field values right there and right now. Now, if the only thing charges ever felt was the electric field, we'd be done. But there's an extra twist, and it's the twist that makes electromagnetism feel like a completely different creature. Moving charges behave differently. Take a charge sitting still in an electric field. It accelerates along the field. Straightforward. Now take the same charge moving through the region. Even if the electric field is the same, The force can have an additional component that depends on velocity. It can push sideways. It can curve trajectories. That velocity-dependent push is what we call magnetism. And already you can feel the confusion growing. Why should the force depend on the speed of the particle? Isn't force supposed to depend on position, not on how fast you happen to be going? Here's the thing. If you want a local field description that works in every inertial frame, meaning any observer moving at constant velocity, then it almost has to be that way, because what looks purely electric in one frame can look partly magnetic in another. Here's the first shock. A magnetic field is what an electric field looks like when you change how you're moving. That sentence is dangerous if you hear it as a slogan, so let's make it concrete. Imagine a long straight wire carrying an electric current. The wire is electrically neutral overall. That means it has positive charges in the metal lattice and negative electrons drifting through. In the lab frame, the total positive charge density and negative charge density balance so electrically it looks neutral at a distance. Yet bring a compass near it and the compass turns. Bring another current-carrying wire near it and the wires attract or repel. That's magnetism. Now here's the detective move. Suppose instead of standing still next to the wire, you move alongside the electrons. You hop on a skateboard and glide along the wire at the same drift speed as the electrons. In your moving frame, the electrons are now roughly at rest. The positive lattice is moving backward past you, but special relativity says something subtle. Lengths contract along the direction of motion. Moving objects look shortened along the motion direction, so the spacing of charges changes when you change frames. That means a charge distribution that was exactly neutral in one frame may not be exactly neutral in another frame. And if the wire is not neutral in your moving frame, then there will be an electric field around it in your frame. Now combine that with another fact. Electric forces exist whether you call them electric or magnetic. A charge near the wire will experience whatever real force exists. The decomposition into electric part and magnetic part depends on the observer's state of motion. So what the lab observer calls a magnetic force on a moving charge, the moving observer can call an electric force because the wire isn't neutral in this frame. That is not poetry. It's a consistency requirement. The force itself must be real and frame independent in the sense that all observers agree on the physical outcome. But how you divide it into E and B depends on your frame. This is why magnetism feels like it comes out of nowhere when you first learn it, because it's the price you pay for making electricity compatible with relativity. If you had only Coulomb's law with instant action at a distance, there would be no consistent way to reconcile it with a universal speed limit and different observers. But with fields and finite propagation, the bookkeeping naturally splits into electric and magnetic components that transform into each other. And just to be intellectually honest, if you're thinking about permanent magnets, like a fridge magnet, there's more under the hood. The stable magnetization of materials depends on quantum mechanics, particularly electron spin, and how electrons arrange themselves in solids. Classical electromagnetism tells you what fields those sources produce and what forces result, but quantum mechanics explains why those sources exist in the first place as stable magnetic domains. So when someone says relativity explains magnets, the careful version is, relativity helps you see why magnetic forces are tied to electric forces for moving charges and currents, and why E and B are aspects of one field, but it doesn't replace the quantum story of why some materials are permanently magnetized, okay? So far we have a field, and we have a weird velocity-dependent piece, but that still doesn't explain our opening magnet and ring trick. Because the ring can respond even when charges in the ring weren't initially moving. You move the magnet, and suddenly a current appears in the ring. Charges start drifting. That means a force appeared around the ring that pushes charges around in a loop. What kind of force pushes charges in circles? An ordinary electric field from static charges usually points from positive to negative. It has sources and sinks. It begins and ends. But a circular push, one that makes charges circulate, sounds like the opposite. It sounds like an electric field that forms loops with no beginning and no end. And here comes the moment where a lot of explanations say Faraday's law, changing magnetic flux induces an electromotive force, and they move on. But that phrase is hiding the real wonder, because it's not just that currents are induced in wires. It's that the universe allows an electric field that curls around in empty space created by a changing magnetic field. If magnetism were just a force from moving charges, then changing a magnet shouldn't create a new pushing field in empty space, but it does. Think about the ring. The ring is just copper. In the beginning, it's sitting there. The electrons inside are jiggling thermally, but there's no net drift. Now you move a magnet toward it. The electrons start drifting in a coordinated way around the ring. That implies a net force tangentially around the ring. Where did that force come from? Not from contact, not from charges building up at one point, because the induced current can exist even if the ring is uniform and there's no obvious place where positive charges pile up. Something is pushing along the loop. The cleanest way to say it is, a changing magnetic field creates an electric field with curl, a looping electric field. The field itself is the agent. Now you might object, but the magnet is the thing moving. The magnet is the source. How does motion of the magnet create a looped electric field? That's exactly the right question, and the answer is the same kind of answer we used earlier. It depends on your frame. If you move the magnet toward the ring, in the magnet's frame, the magnet is stationary and the ring is moving toward it. In that frame, the charges in the ring are moving through a magnetic field, and moving charges in a magnetic field feel a force sideways. That sideways force can push charges around the ring, so in that frame you can tell a magnetic force on moving charges story. In the ring's frame, the ring is stationary and the magnetic field in the region is changing as the magnet approaches. In that frame, you tell a changing magnetic field creates a curling electric field story. Same physical result. Charges circulate. Different decomposition of cause. Magnetic force in one frame, induced electric field in another. The underlying reality is unified. Your language splits it. That's a deep lesson. If you try to insist on a single cause in one single language, you will get confused. Electromagnetism is not one force and then another. It's one field and its local rules. Now we can sharpen the deal we made earlier. We want a local rule book for fields, not a magnet affects a ring, but what must be true at each point in space so that rings react, currents produce magnetism, and observers agree. Let's list what we've discovered so far, like detectives pinning clues to a board. Clue 1. Charges create electric fields. Those fields point away from positive charges and toward negative charges. That's the static part. Clue 2. Moving charges and currents produce magnetic effects, and magnetic forces depend on velocity and are perpendicular to the motion and the magnetic field. Clue 3. Changing magnetic conditions can produce a curling electric field that can drive currents. Now you might think this is the whole story, but it's not complete, because there's a symmetry missing. We have a rule that says changing B produces curling E. But do we have a rule that says changing E produces curling B? If we don't, then the story is lopsided, and nature tends to punish lopsided stories. Maxwell noticed a tiny inconsistency in the rules, and fixing it accidentally predicted radio, light, and every wireless signal you've ever used. Let's approach this the way Maxwell did, but without drowning in equations. Imagine you have a capacitor, two metal plates separated by a gap. You connect it to a battery. Current flows in the wires, charges accumulate on the plates, and an electric field builds in the gap. Here's the puzzle. In the wire leading to the capacitor, current exists. Electrons drift. That current produces a magnetic field around the wire. You can measure it with a compass. But between the plates, there is no conduction current. There's a gap. No electrons cross the space like a river across a bridge that doesn't exist. Yet the magnetic field around the wire does not abruptly stop at the edge of the plate. The whole configuration has to be consistent. The field lines of magnetism must form continuous loops around what we call current. So what counts as current, really? If you define current only as charges moving through material, then the magnetic field story breaks inside the capacitor region during charging. The magnetic field would have nowhere to come from, and worse, the mathematics would become inconsistent with charge conservation. Maxwell's fix was conceptually simple and profoundly weird. A changing electric field acts like a kind of current for the purpose of creating magnetic fields, not because charges are literally crossing the gap, but because the changing electric field in the gap contributes to the magnetic curl in exactly the way needed to make the laws consistent. This term is called the displacement current, but don't get distracted by the name. The heart of it is changing E produces B. Now look at what we have. We already had changing B produces a curling E. That's induction. Maxwell adds changing E produces a curling B. And now if you put those two together, you get a runaway effect that isn't runaway. It self-propagates. Picture a region of space where for some reason the electric field starts changing. That changing E produces a magnetic field curling around it. But a changing B produces an electric field curling around it. If these changes feed each other in the right pattern, you get a wave, a coupled oscillation of E and B that travels through space. No charges required in the space where the wave passes, just the field changing locally and pushing the next region into changing. This is why light exists in the electromagnetic theory. Light is not a different ingredient. It's electromagnetism doing its own self-consistent dance in empty space. The stadium wave analogy helps here if we use it carefully. In a stadium wave, no person runs around the stadium. Each person just stands up and sits down in response to their neighbors. The pattern moves because of local coupling. The wave is a pattern that propagates. Similarly, in an electromagnetic wave, no substance is flowing through space like wind. Instead, at each point, the electric and magnetic fields change in time according to the local rules, and that change triggers changes nearby. The pattern propagates. Now we can connect this back to the speed limit. The coupling strengths between these field changes set a propagation speed, and that speed is the speed of light. It's not that light happens to go at some speed and electromagnetism is separate. The theory predicts that electromagnetic disturbances propagate at that specific speed, and light turns out to be one of those disturbances. This is one of the most satisfying moments in all of physics because it's not a coincidence. It's a unification. Electricity, magnetism, optics, radio, one set of local rules. But we still owe ourselves something. In our opening magnet and ring story, energy moved. Where was it? What carried it? Because if you think like a beginner, you might say the electrons carried the energy. They moved, so they delivered energy. But here's a number that will change your intuition. In a typical household wire, electrons drift incredibly slowly, millimeters per second, yet when you flip a light switch, the lamp lights up almost immediately. Not because electrons from the switch rush to the lamp at near light speed. They don't. The electrons were already in the wire. What changes rapidly is the electromagnetic field configuration throughout the circuit. So where does the energy flow when a circuit powers something? When a lamp lights, the energy doesn't march through the copper like soldiers. It appears because the field around the circuit rearranges and delivers energy into the filament. This is the same kind of truth you saw in the magnet and ring experiment. The energy transfer isn't best described as stuff traveling through the wire. It's described as energy in the field, moving through space and into the device. Now, saying energy is in the field can sound like mystical fog if you don't pin it down. So let's pin it down. Fields are measurable. The electric field has a strength at each point. The magnetic field has a strength at each point, and there is an energy density associated with the fields. Stronger fields mean more energy stored per volume. If you have a capacitor with a big electric field between the plates, there's energy stored in that region, not in the metal, not in the battery, but in the field configuration. Likewise, around a current-carrying wire, there's a magnetic field, and energy is stored in that magnetic field. And when fields change, energy can flow from one region to another. There is a precise quantity called the Poynting vector that tells the direction and rate of energy flow in the electromagnetic field. But even without writing that formula down, you can understand its meaning. Energy flows where electric and magnetic fields coexist in certain orientations, and the energy can flow through the space around conductors into components. This is why the water in a pipe analogy for electricity is simultaneously useful and misleading. Useful because currents do behave like flows and have conservation. Misleading because the energy transfer is not simply kinetic energy of drifting electrons. The electrons in a wire are like a crowd shuffling. The crowd's slow drift is not what transports the announcement from one end of the stadium to the other. The announcement travels as a wave of influence, an electromagnetic signal that moves near the speed of light along the circuit, guided by the conductors in geometry. The electrons respond locally, rearranging in tiny amounts, establishing fields that propagate the signal. So now we have multiple threads that want to tie into one knot. Electric fields describe how charges are pushed. Magnetic fields describe additional velocity-dependent pushes and show up naturally when you demand relativity consistency. Changing magnetic fields create curling electric fields, induction. Changing electric fields create curling magnetic fields, Maxwell's fix. Coupled changes propagate as waves, light. Fields store and carry energy, explaining how energy moves in circuits and induction setups. All of that is one story. So the one explanation is this. Electromagnetism is the set of local rules that tell a single physical field how to exist, how to change, and how to push. Let's say that again, but even more concrete. At every point in space, there is something you can measure with test charges and test loops, the electric and magnetic field values. Those values tell charges how to accelerate via the Lorentz force. The fields themselves are constrained by source rules. Charges create divergence in the electric field, and currents in changing electric fields create curl in the magnetic field, and changing magnetic fields create curl in the electric field. And magnetic field lines don't begin or end in isolation the way electric field lines can. If you accept those local constraints, everything else falls out. The ring reacts to the magnet because changing magnetic conditions force a curling electric field. The compass turns near a wire because currents create a magnetic swirl. Light exists because the field update rules allow self-propagating waves. Circuits deliver energy because the field carries energy and momentum. And here's the payoff that's easy to miss. This is not just a tidy mental model. It's a replacement for action at a distance. It's how you make physics local, causal, and consistent with relativity. Now, at this point, a reasonable person asks the question that always comes next. Okay, but what is the field physically? Is it a substance? That's where we have to be honest. In classical physics, the field is treated as a real physical entity because it carries energy and momentum and because the dynamics are local. But asking what is it made of is like asking what is a wave made of without specifying the medium. In electromagnetism, the field is the medium. There isn't a deeper classical substance underneath. In modern physics, the electromagnetic field is a fundamental object, and in quantum theory, it has quantized excitations we call photons. But that doesn't make the classical field fake. It makes it the large-scale, average description of something that can be more granular. So you can be satisfied in two ways. If you want a practical mechanism for everyday phenomena, magnets, circuits, radio, light, then the field as a real local entity with update rules is the mechanism. It's not a label. It's the thing doing the pushing, and it's the thing carrying the energy. If you want a deeper answer about why does the universe have this field at all, then you're stepping into the territory where physics becomes more like archaeology. We have deeper layers, quantum electrodynamics, gauge symmetry, the structure of interactions. But even there, at some point, you hit bedrock. The field is part of the bedrock. And that is very Feynman-like. You can go down and down in explanation, but eventually you reach a set of rules that describes what happens, and the question why these rules becomes a different kind of question, a philosophical question or a question for a future theory. But the title promised something else. No one can explain electromagnetism like this. That promise should feel fulfilled, not because we claimed secret knowledge, but because we reorganized the story into one coherent mechanism. So let's go back to the opening scene and watch it again with new eyes. You slide the magnet past the copper ring. The magnetic field in the space near the ring changes. The local rules say, a changing magnetic field produces a curling electric field. That curling electric field, D, pushes charges around the ring. Those moving charges constitute a current. That current produces its own magnetic field, which can oppose the change that created it. Energy flows from your hand doing work moving the magnet into the electromagnetic field configuration and into heat in the ring, or into mechanical motion if the ring pushes back. Nothing touched, but nothing violated locality either. The influence passed through space as a field change obeying a speed limit. The action was in the field. You don't have to memorize electromagnetism. You can recognize it whenever reality enforces a speed limit on how influence spreads. The moment you see a force that acts without contact but still respects causality, you're seeing a field. The moment you see effects that depend on motion and frames, you're seeing the unification of electricity and magnetism. The moment you see a changing condition create a looping push, you're seeing induction. The moment you see something propagate through empty space carrying energy, you're seeing electromagnetic waves. And maybe the best way to check whether you actually understand it is this. Try to explain magnetism to yourself without saying because magnets, and without saying because relativity as a magic word. Say instead, there is one electromagnetic field, and observers slice it into electric and magnetic parts depending on motion. The field's local rules are constrained by sources and by consistency, and once those rules exist, everything else is inevitable. That's the kind of explanation that turns electromagnetism from a chapter in a textbook into a way to see reality. Because the next time you use a phone, you can picture it, not signals traveling in the air as a vague thing, but actual electromagnetic waves, self-propagating patterns of E and B, carrying energy and information, reflecting, diffracting, interacting with antennas that are just clever ways to couple to the field. And the next time you watch a light turn on, you can picture it, not electrons racing from the switch to the bulb, but the field rearranging through the circuit geometry, carrying energy into the filament where it becomes heat and light. And the next time someone says it's just invisible forces, you can say, no, it's local rules for a field, and the field is as real as anything else in physics, because it carries energy and momentum, and it's the only way we've found to make the universe causal. That's not just knowledge. That's a new lens,